Yeah, let's start. Cool. Okay, cool. So my name is Sophie, and I'll be hosting the workshop today on the Introduction to Mathematics. Just to give some context as to why I'm giving a mathematics workshop, I work here at Lift 99 on a startup called Vermio, which focuses on digital health for pregnancy health. But by training, I'm an applied mathematician. I have a master's degree in mathematics from Sydney University that I got back in Australia before I moved to Thailand. And so today we're going to do an introduction to mathematics, to go through some key areas in maths that are quite important. And really in one workshop you can't really cover the whole of mathematics, so today we're going to focus mostly on number theory, starting with prime numbers, complex numbers, and then using those two concepts to talk about something called the Riemann hypothesis, which is one of the most famous unsolved problems in mathematics. So yeah, we'll see where that leads us. But to start with, I thought we'd do a bit of a warm-up just to kind of get our minds more working in a mathematical mindset and doing some puzzles and that type of thing. And also to explain some of the key areas of mathematics and some of the key mathematical concepts. So what is mathematics? The way mathematicians perceive maths is a bit different probably to how you were taught it at school. Most people from school say that mathematics is something where they did a lot of rote learning and exercises in a repeated way. But for mathematicians, mathematics is something a lot more deeper than that. Mathematics is more like a creative thing. I think someone's got their microphone running. No, not sure. Okay. Yeah.
You can say it like, please
hello?
mute microphone.
Whoever's got their microphone on, could you please mute your microphone? Okay, I think that worked. Cool. So
inside the speech.
Hello?
It's a bit hard to follow this really fast English, especially if I don't see you.
Oh, I can speak a bit slower if that helps.
Thank you, yes, thank you.
Okay, cool. Yeah, and sorry you can't see me. For some reason I can't share both the screen and the video at the same time.
Okay,
cool.
Okay, just slower, okay?
Sure thing. Okay, so back to what is mathematics. So for mathematicians, mathematics is a creative discipline, and Einstein once said that mathematics is like the poetry of logical ideas because it's both very creative but also very structured in that there's a lot of logic, a lot of proofs of proving different mathematical theorems using a logical system. But I think for a lot of people, during school, mathematics wasn't really conveyed this way. It was conveyed more as a series of very confusing rote exercises. And so today I'm hoping to teach you more about the creative side about mathematics and how mathematicians actually perceive the discipline. So to start, mathematics you can think of as having three major disciplines, but at times these disciplines often intersect each other. So in mathematics we have number, the study of numbers. We also have shape and geometry, and also change, which is where calculus comes into it. But at the same time, even though there's these three distinct disciplines, you can think of there's many areas in mathematics that overlap and combine lots of these things together. A second way to think about mathematics is in terms of these more abstract concepts. So while you have branches of mathematics like number, shape, and change, you also have these kind of abstractions of how mathematics works. So for mathematicians, mathematics is a lot about elegance. So there's a lot of beauty in the types of proofs that mathematicians write and discover. There's also a lot of mystery to mathematics. There's a lot of very big problems in maths that haven't been solved for centuries. And this really creates a lot of wonder among mathematicians to try and solve these problems and wonder why these problems are so hard and what kind of secrets can we uncover if we're able to solve these really challenging problems. And then finally, utility. Mathematics has so many applications in the real world, things from physics to engineering, the finance and economics. Like the applications of mathematics are quite boundless. And so these are really, I guess, the three pillars of mathematics, the way mathematicians see it. There's some dimension of elegance, mystery, but also utility, and that you can apply a lot of these ideas to real world problems. So we're going to start with a bit of a warm-up to get our heads around these different ideas. So we're going to go through each of these three areas of elegance, mystery, and utility. So to start with elegance, I'm going to get each of you to try and solve this problem. So hopefully you all have a bit of paper. If not, grab a pen and paper. And I'm going to set a timer for 5 minutes, and you can solve this in any way you want, but try and come up with an answer to how many triangles are in this shape. And also, I'll also give everyone a sticky note that they can write their answer on. So by the end of the 5 minutes, you should come up with a single number answer. And it's completely anonymous, but I'll stick them all on the board and kind of we can vote on what we think the answer is. Yeah, okay, you cheat them.
I remember I did once this.
You
I
think?
don't remember what was the number.
Okay, time's up. Okay, just write whatever answer you have on the sticky notes. It's anonymous, so no shame.
Yeah.
Okay, so I got 72, 44, 40, a few different answers here. Another 40. What's this? 64 plus 8 minus 72. And 44. Well, what does that actually come to?
Even more biased for mathematician.
Huh? Well, okay, that's lower than these ones. Anyway, the correct answer is 44. So how many people? Okay, 2 people got that. Cool. And 40, 2 people do 40, which is kind of close. We'll go for the answer. So yeah, my point of asking this question is not so much to count the number of triangles, but to learn how mathematicians would think about this type of problem. Because there's many ways you could solve this. Does anyone want to share how they solve this?
From biggest triangle to smallest.
Yep, so you kind of started with these ones here
Yes.
and zoomed in. That's fair. Anyone else got a different approach?
There's also a repeating pattern, basically. There are similarities. The 4 are the same, and the big one also has the same pattern. So you can kind of work with that.
Yes, precisely. There's lots of patterns in the shape, and you can kind of leverage that to come up with the answer. Cool. So I'll go through how a mathematician would think about this, which is quite similar to what you're saying about the patterns. And basically, if you look at this shape, in mathematics language, we would say this shape has a rotational symmetry of order 4. And what that means is that if you take any of the triangles in the shape, so say this one here, and you rotate it around the shape itself, once you rotate it 4 times, it will come back to where it starts. You do the same with any of these triangles here. Like this one, for example, you rotate it, it comes up here, there, down, and then back around. It has a rotational symmetry of 4. So any triangle in this shape can be rotated around itself 4 times. So using that logic, the answer to this question has to be a multiple of 4. It has to be some number where 4 divides evenly into it, because the shape itself is very symmetrical and everything is an order of 4. And so using that, you can try and break this down a bit further into the different types of triangles you see in the shape. And so there's a lot of these smaller ones, which are usually the most obvious ones to spot, and there's 16 of these. There's also 16 of these larger ones, 4 of this type in each of these quadrants, and 4 of those, and 4 of the large ones. And so once you add all those together, you get the answer of 44. Does that make sense to everyone? How we get to that?
Yes.
Any questions? Cool. So what this means about elegance is that when you're solving a problem in mathematics, you can arrive at the answer using many different approaches. You can look at this shape and sit there and count as many triangles as you can, or you can think about it from a different perspective and try and look for some kind of patterns or symmetries in the shape itself. So that's what elegance is about in mathematics, not necessarily coming to the right answer, but also having the most elegant approach to doing it. And by elegance, we mean a method that doesn't just arrive at the answer, but also tells us something interesting about the problem. So in this case, understanding symmetries tells us something interesting about how symmetry works in geometry. So that's the elegance aspect. Moving on to what mystery is. So in mathematics, mystery is about asking the big questions. So we had this small shape here, but a bigger question we could ask in the context of this problem is, so what happens if we put 4 of these together and make this larger shape? And what are the number of triangles in this case? If we make an even larger shape by putting 4 of those together, how many triangles are in this shape, and so on? And are we able to find a pattern that no matter how many of these squares we put together, we have some kind of general formula where we're able to know the number of triangles? So that's kind of like the mystery aspect of mathematics, asking these big questions and trying to develop methods to solve it. So if someone gave you this problem to find how many triangles in the shape for any number of n, how would you go about that? Does anyone have any thoughts?
Recurrence.
Recurrence?
Proved by I don't know how to say
Oh,
it in
recursion.
English.
Recursion?
I don't know how to say it in English.
Fair. I think I know what you mean. I think
Or I need to check on the
Repetition, perhaps.
Repetition, yeah. Look like,
No, I need to check.
okay. But how many triangles, what do you mean? Should we find there, or what?
yeah, so in this shape, there were 44 triangles.
Mm-hmm.
And if we're looking at this shape now, how many triangles would be in this
I
one?
think that you should, you have how much squares you have within this pattern, the N4?
You think
so
it's that times 4?
No, you must to make it, n multiplied by 4 and plus 1 more, like this.
There's like plus more. Yeah, I see what you mean. So to start with, there's going to be that times 4, just because it's 4 of those.
It's minimum.
Yeah, that's and then
you must divide also the biggest one to plus something, like.
That's fair, because there's going to be more triangles, because just by making this larger shape, there's going to be a big triangle here, for example, that didn't exist
So
here.
base is the number of triangles in the simple one, and then you
Yeah, you have to find add, but you have to find what to add. Yeah.
Yes. But there must be a formula. There must be a
Recurrence relation.
dependency.
Recurrence relation. Yeah.
Recurrence relation doesn't
How?
make sense. Recurrence relation.
Well, what's it called in French?
Huh?
Is it called the same thing in French? Or?
Yes.
Interesting.
Yeah, there's some kind of relationship that you can write as a formula. I don't know what it is, I haven't solved it. I'm just posing the problem here just to ask you to think about how you would solve it. But one method perhaps you can use is you can use a computer, for example, to code how many triangles would be in these shapes, and use that to look at the pattern for larger and larger triangles, and then try and find a pattern in that. So there's many ways you can approach it. There's never one approach to the solution. But that's basically what mystery is about. It's about asking large questions, often in the limits of infinity. What happens in a very large scenario? Are we able to solve this? And sometimes it's not always the case you can even solve the problem. And then finally, utility. So why does counting triangles matter? Why do we do this? Does it have some application in the real world? Well, it turns out that it does. I actually did my master's thesis in a discipline of mathematics called network science, and my thesis involved writing lots of algorithms to calculate the number of triangles and shapes for networks that are relevant to real world problems. So the next question I'm going to ask is, does anyone know what this is?
Flights.
It's a good guess, flights.
Yeah.
It's not, but it's a good guess.
Maybe this is the internet.
Another good guess, but it's kind of is the internet, but a certain aspect of the internet.
It's a cold phone.
Not quite.
Kind of internet. Some network. I don't know what it is.
So it's a Facebook network.
Mm-hmm.
So internet was quite close, but basically, it's a bunch of Facebook accounts of people who live across Europe, and there's a line between them if those two people are friends on Facebook. And so this is showing the interconnectedness of the Facebook social network throughout Europe. And Facebook researchers did a research study on this because they wanted to find if there were any interesting patterns of how people socialize and communicate in Europe. And they found some interesting trends, like every August, Europeans tend to make more friends with Europeans from other European countries, because in August, that's when people travel during the summer and tend to travel the most. And other interesting things they discovered about places that share a common language tend to have more connections between each other. So people from countries that speak a similar language, and also countries that are closer together, people also tend to have more friends.
Except Estonians, they don't.
Yeah, except these people here have no friends. No. So yeah, it was quite interesting. But how's this related to triangles? Well, interesting thing is that when mathematicians who study networks, when they want to understand how interconnected a network is. So for example, if we ask how interconnected are friendships across Europe compared to friendships across the United States, we calculate this thing called the clustering coefficient, which is calculated by finding all the triangles in this network. So the mathematicians will go and count every single triangle, or they'll use an algorithm to do that. They won't sit and count them all. And then they'll multiply that by 3 and divide that by the number of triples in the network. So I'll explain what that is. So, oops.
Can we apply this formula to the counting of this square?
Yeah, you could, because that's a network. Yeah.
So,
But that would tell you, so this formula itself doesn't tell you the number of triangles. I don't know, so let me go back.
could we try now?
Well, you could if you want, but what the formula tells you is how clustered the network is. So how interconnected it is. So for example, here, if this is a network and it's not very connected, maybe these are the only connections, it's not very connected. But if we have one here where every single node in the network is connected to every other one, this one is more connected, so this would have a higher C coefficient. So C is like the amount of interconnectedness within the network. So what the researchers at Facebook were trying to measure was how interconnected relationships were between different countries and across countries as well. And so they figured out that, well, they didn't figure this out, someone else did, but the formula is 3 times number of triangles in the network by number of triples. So this n triangle here just means like number of triangles in the network, and this n3 is called the number of triples.
So
What triples is, it's a triangle that isn't closed. So in this network, for example, there's a triangle here, because these 3 things are connected together. So that's a triangle.
The first one, C is 0.
Yeah, because there are no triangles. But there are triples. So what a triple is, it's when 3 things are connected, but the triangle is not necessarily closed. It can be, but it doesn't have to be.
So every node is a Facebook account?
Yep.
Okay.
Yeah, so every node in that network is someone's Facebook account, but only for people within Europe.
So you need to know number of triangles.
Yep,
How you know?
you have to count them.
Manually.
Well, they'll like write a program and pretty much they'll write a for loop and count over the number of triangles using
The
code.
interpretation of interconnect is
Yeah, so the interpretation is that if you think about it in terms of friends,
I'm friend with you, I'm friend with
yeah, so if
Leon.
there's like A, B, C,
So friend.
these are the friends. If A is friends with B and B is friends with C, often what happens in social groups is that people are friends with their friends. So if you have a group of friends who all know each other, all these people are all going to be connected in a network. So if this is one of your best friends, so you're A, one of your best friends is B, your other best friend is C, and C also knows B, then that forms a triangle between the 3 people. Does that make sense?
Yeah.
It does.
Yeah. And so what often happens is in social networks like Facebook, a lot of people may know each other because, say, they went to school together. So you have a whole cluster of people, say all these people here, who all went to the same school. So everyone here all knows each other and they're all interconnected. So each of these dots is like each of the people in this class. and the lines of who's friends with who. But then you have a group of people who went to a different school, and these people are also probably very interconnected because they go to school together, but maybe only one person from the other school knows someone from this school. So that's basically how networks work. And the reason they count the triangles is because the triangles represents the relationship of someone who's your friend also knowing another friend and knowing you. And so it's an effective way of capturing the interconnectedness of a network and finding these types of communities within either classrooms or large-scale global social networks.
Great for coronavirus.
Yeah, it is used a lot in epidemiology to look at the spread of diseases. There's a model called, I think, SIR model.
You mean these networks that are really interconnected are good for coronavirus?
Not good for coronavirus, but good for understanding the spread of the virus.
I mean, that's awesome. More you're interconnected,
One hub is
more
like, I don't know, London, the other hub is Tallinn, and then...
Yeah, so you could pretend this is, for example, the people who have coronavirus and which person was in contact with who when they were infectious with the disease. So say someone from Tallinn was, I don't know, in Russia and infected a lot of people here, then a link would form between those people. And so by understanding the clusters of the network, you could find the hotspots of where the virus is likely to be more problematic at that point in time.
London.
Yeah. So it's quite useful.
They are all from London.
All English
Well,
people seem to travel.
These people seem to make a lot of friends from
and they can
everywhere.
speak English.
Yeah, so I guess in Europe, people from London are most interconnected to the rest of Europe in terms of friendships.
It's a financial hub, so makes sense.
That's true.
Interesting that Estonia is so much like isolated.
Exactly, that's why it has...
Estonia and Finland are
It's
quite lonely.
surrounded by void or something. Surrounded by
You
void.
need to make more friends with people from London. So yeah, that's one real-world application of why counting triangles would be useful, is to try and understand relationships like this. So that basically sums up what I mean by this elegance, mystery, and utility thing. By the elegance, we have the pursuit of the most simple solution to a problem. It also offers some insights about the problem. By mystery, we ask the bigger questions about the problem, and often these problems are unsolved. Things like the Riemann hypothesis is an example of a very large mystery in mathematics. Mathematicians really want to solve it, but they haven't yet been able to. And also utility. Often some of these concepts we developed in an abstract way by solving puzzles can have some use in the real world. So, moving on, that was kind of like the warm-up and introduction to mathematics. For the rest of the session, we're going to focus mostly on number. Because we can't really cover everything in one session. I think number is one of the most interesting areas of mathematics to start with. So actually, if you want to explore some more aspects of mathematics, I can send some links around at the end of this talk, but this Quantum magazine has this map of mathematics, and it's a useful tool for exploring all the other areas as well if you want to go beyond number.
Quantum magazine, that's fascinating.
Yeah, Quantum magazine is fantastic. It has really good articles about maths and physics and other things. So it's a good resource if you want to explore the other area number. So we're going to start with the prime numbers, move on to a concept called complex or imaginary numbers, and then finally talk about this problem of the Riemann hypothesis. So we'll probably take a bit of a break after prime numbers and then come back and do the other two topics. So who remembers prime numbers from school or uni? No one?
I remember them, but
but you don't remember what they are?
Not from school.
Okay.
By definition, it can be only divided by itself or one.
Yes,
Yes.
correct. Yep. So these are some prime numbers here. And so prime numbers are...
12 is not a prime number because it can be divided.
Yes.
By 6
Yeah, so
And 2
and 4.
and 3.
2 is defined as a prime number.
How much triangles in 12?
Yeah, so basically a prime number is any integer whole number that's larger than the number 1, but not divisible by any whole number aside from itself. So as you say, something like 12 is not a prime number because you can do 6 times 2 is equal to 12. And other numbers, for example, like 15 is 5 times 3 is equal to 15. And so these are not prime numbers. But these numbers here are all primes because there's no other factors that can be divided into these evenly. And so in mathematics, we like to think of prime numbers as the atoms of arithmetic. In the same way that particles are like the atoms of physical matter, prime numbers are like the atoms of numbers. And so the reason for this is that there's this fundamental theorem of arithmetic that was discovered back in ancient Greece, 300 BC, that every single number or whole number greater than 1 is either a prime number itself or it's a unique product of primes. So what's that mean? So basically, if we take any whole number, like say the number 12, we know this is not a prime, but according to the fundamental theorem of arithmetic, this is actually a product of primes, which means that you can take some prime numbers, multiply them together, and you'll get 12. So does anyone know any primes that would multiply to 12?
Yes.
Surprise you.
3, 4.
4 is not prime.
No, maybe I didn't understand the question.
3 times 2 times 2. I have to be
Yes,
primes.
yes, I did
Yeah, you do, kind of.
That's the wrong. Yeah.
Can you repeat the last one?
So if you take any whole number, so it's using 12 as an example, you can pick prime numbers that will multiply together to give the number 12. So these are some of the prime numbers here, these ones here. And if you multiply some of them together, you have to pick which ones, they will get to 12. So if you multiply 3 times 2 times 2, which are all prime numbers, that equals 12. Not be explained again.
Yeah, I'm just thinking it's really.
So 3 times 2 times 2 equals 12, right? You agree with that?
Yeah.
Cool. So these are all prime numbers as well. So if you take any single number, it doesn't have to be 12, it could be anything. There's a way of multiplying prime numbers together that will get to that number.
Mm-hmm.
So if we take another number like, I don't know, 8 or something, there's a way of choosing prime numbers that will multiply together to get 8.
Yeah,
So in this case, 2 times 2. They're both prime numbers, yeah.
Oh, one.
Oh, sorry, 2 times 2 times 2. So yeah, same thing here. Take a number like 15. Anyone?
3 by 5.
Yeah, 3 by 5. They're both prime numbers. And you can do this for large numbers, any single number. There's a way of finding some prime numbers that multiply together to get that number. So that is the fundamental theorem of arithmetic, and also the reason why mathematicians consider the prime numbers to be like the atoms of number, because any number you pick, you can make that number using primes.
But also, I remember something, maybe I'm wrong, that you can find prime number by multiplying the prime numbers. No, it's another thing.
Okay.
I mean, something, there must be not this thing.
There's lots of conjectures. We'll go through a few more.
Multiplying prime numbers is great, but that's later.
That's later. Yeah, multiplying prime numbers gives you how our whole encryption systems work, but we'll get to that a bit later. But yeah, going through our history of prime numbers, so that was from ancient Greece. Also, from ancient Greece, we got the theory that there's an infinite number of primes. So going back over here, here's a list of prime numbers, but this list goes on further and further. There's more prime numbers after 17. For example, 19 is another prime number. There's more prime numbers after that. If we just Google, no, I'm not going to Google. Never mind. Like this, if you Google list of prime numbers, you'll see that this list goes on forever. It never stops. The number of prime numbers is infinite. There's no end to this list. So that was also one of the discoveries that was made around the time of ancient Greece. We're going to come back to this a bit later, and we're going to look at why this is the case by looking at the proof for why this is so. But I guess now, just keep in mind, the list of primes never ends. The primes are infinite. And so between ancient Greece and 1700s, there wasn't much learnt about primes, but there were a lot of mathematicians around like the 16th, 17th, 18th centuries who were quite interested in prime numbers and discovered lots and lots of stuff during this time. So one example is a thing called the Goldbach Conjecture, which to this day still remains unproven. This means that mathematicians think this is true, but they haven't proven why this is the case. And the theorem is that every even integer, so even integers are ones that can be divided by 2, every even integer greater than 2 is the sum of 2 primes. So for example, if we take any even integer, a number 8, we can add 2 prime numbers together and get to 8. So,
3, 5.
yep. And that's the case for any even integer. And mathematicians discovered this in the 1700s, but haven't been able to yet prove this formally. And then that leads us into the time of Riemann. So 1859, mathematician by the name of Riemann made a lot of discoveries about prime numbers, and he wrote this paper where he was able to shed a lot of light onto how prime numbers are distributed. So if we look at the pattern of the primes, so just looking back here, it's pretty much impossible to see a pattern and determine which number comes next, just looking at this list. For small numbers, people often look at it and think, oh, it looks like the odd numbers, but as they get larger and larger, that's not the case. There's a lot of odd numbers that can be divided by things, like 15, for example, is not a prime number. So mathematicians have never been able to find a single rule or pattern to this list to figure out which number would come next. So what the Riemann hypothesis does, it's basically our closest way of coming close to understanding the pattern of prime numbers. So we're going to come back to the Riemann hypothesis later and go into that in more detail to understand why that is the case. But after the Riemann hypothesis was discovered or conjectured, mathematicians were able to assume if this can be proven this is true, we can understand a lot of other things about prime numbers. And this is when the prime number theorem was discovered in 1896, which tells us how often prime numbers occur. So as the prime numbers get larger, because there's an infinite number of them, so there's some very large prime numbers, they tend to occur less common as they get larger. So this was proven in the 1800s, using the results from Riemann, if we can assume they are true. And basically, what the prime number theorem says is that there's this function, which we denote by pi n, but it's just a function. And that's the number of prime numbers that are less than or equal to n.
Wait, what?
We can go through that in a bit more detail.
Yeah, it's simple.
So pi n,
Yeah.
number of primes that are less than n. So if we look at pi 10, that is the number of prime numbers that are less than 10.
5,
Yeah,
7.
5, 7. So pi 10 is the prime numbers less than 10.
Yeah.
These are all less than 10. So pi 10 is actually equal to 4 because there's 4 numbers. That's what pi n is.
So how much prime numbers contains this particular number? Yeah, or
Yeah, it's how many, so if we take the number 10, how many are less than 10? There's 4 prime numbers less than 10. And so mathematicians discovered that this function looks like this, n over the natural logarithm of n. When you, don't have to worry too much about that, but when you plot that, it looks like this. And because of the way it curves over, as the prime numbers get larger, there's less and less prime numbers. They become more spread out. So that's what that was about.
what is the largest prime number known today?
Well, glad you asked. This is the largest one, this one here. According to this graph, it has 10 to the power of 7 digits in it. So I'd hate to think how big that is. That's a very, very large number. So sometime in the 1990s, I think, because we had computers and we can do really cool things with computers, mathematicians set up this project where people could share their computers to work out the largest prime number by running some algorithm on their computer to keep searching for larger and larger prime numbers. And so it was discovered at some point in time that a lot of prime numbers have this format where you have 2 to the power of some number minus 1. And these are called the, I don't know how to say that, Mersenne primes. A lot of prime numbers, not all of them, but a lot of them take this format. And when you're using a computer, it's much easier to validate that these numbers are prime. And so a lot of people started looking for prime numbers of this form. And so today, this is the largest one we've found so far, but people still got computers running with this program to find even larger prime numbers.
Once I was writing an algorithm to find new prime numbers, but I don't remember what was the result. Is there any formula how to find a prime number, or I need to validate it manually? if I assume that this is prime number, that next number is a prime number, then I must divide it by every number before in the list, and then if they all fail, that means it's
Yeah, so you can
prime
do it
number.
very slowly and start dividing it by every single number
Is
before
it
it.
like this now? How they calculate?
The reason they try and find numbers of this format is there is a faster algorithm where they've proven you only have to validate so many numbers, like a subset of numbers instead of all of them. That's the main reason why they like to find numbers of this format, because it's a lot quicker. You won't have to divide every single number.
You actually skip some numbers
Yeah.
by this formula.
Yeah, so by
But still, you need to go back and take
Yeah.
old numbers.
which is why it takes so long. I mean, even looking today,
It's a huge operation. It will take days, maybe
Well,
for this number, no?
years.
Yeah.
Oh yeah, for that number alone, yeah, I think it took a few months or something to validate it.
To validate.
Yeah, so every time they find a new number, they someone on one computer may find it, and then they get someone else with a different computer to revalidate it, just to check it's actually prime, and it takes a few weeks just to do that. And there's usually like,
Before I go, more it takes
Hmm?
time. I mean,
and as larger it gets, the longer it's going to take.
Your computers are getting faster as well, hopefully.
Well, that's why in this curve here we see like a big jump where computers got a bit better here. But oops. So yeah, if computers do get a lot better, if we have a quantum computer to do this,
Does not look promising.
it doesn't. So we need quantum computers somewhere here too. So yeah, it's quite interesting. But there's always this search on for the next prime
interesting
number.
that also, though, some scientists they try to find the formula for the finding the prime number. But these all they fail.
Yeah, you
So
can't.
There is no formula for finding a prime
The
number.
closest thing is the Riemann hypothesis, but it still in itself doesn't give you a formula. So yeah, no one's ever been able to find the formula. And if you discover that, then you can like have $1 million.
Goldbach Conjecture.
Oh, that was the one that
I didn't get it.
every even integer greater than 2 is the sum of 2 primes.
Every even integer greater than 2.
Yeah, so
Okay. Yeah.
yeah,
Conjecture.
We can go
Okay. It seems I need to translate the word conjecture.
it's kind of like a theorem.
Like also theorem, yeah?
Yeah, also a theorem. Yeah.
Conjecture. Okay. In Russian it's догадка.
Okay.
It means that it's another mathematician that is.
Goldbach was a mathematician, and he was like, it was his guess. Like, conjecture is a guess.
Yeah, so we can't call it a theorem. It's the same with the Riemann hypothesis. We say hypothesis because it's not proven yet. So when we prove it, we can call it theorem. Until then, it's like just
When you use
conjecture.
hypothesis and conjecture, are
No.
they different?
They kind of mean the same thing.
Same.
Yeah.
So
It's only when it's a theorem. So the prime number theorem was actually proven, so we can call that theorem because we know it's true. So
but
that's,
they are infinite numbers.
no, that's the infinitely many prime one. Prime number theorem is how often they occur. So they occur less often as they get larger.
Okay.
Yeah.
Just this one.
Yeah.
Yes, that's.
It
You see it
intuitively
in
makes
practice.
sense.
Yeah, that makes sense. If you look at the first few prime numbers, they're only like 1 or 2 digits apart. As they get larger, like these ones here are
But
very
about
far
this
apart.
prime number theorem, it was proven, yeah?
Yep.
But why there is such situation when you have, for example, a long period, I don't know how to name it, period maybe, then you don't have prime numbers there, and then you meet like few of them right away.
It makes sense. Think about it as combination. Since the numbers are tonic, the more prime numbers you have, the more combinations of those prime numbers you can make. Therefore, the more non-prime numbers you can generate in between them.
Yes, but sometimes you meet like few numbers in a row or something like this. Not
It's
few
just
numbers.
chance. I mean, the prime number theorem is more an average thing. It's not necessarily the next number will be further away than the previous number. It just means on average it will
Actually,
be.
$1 million question. What, yeah.
That one.
Distributed.
Yeah. Yeah. There's a lot of $1 million questions that are related to prime numbers.
A lot of different
$1 trillion questions if you can solve some of them.
Or if I answer.
If you answer it, you can probably
If
find
you-
ways to
if
apply
you
it to pay
answer
yourself.
You can hack every single computer system in the world.
Okay, you could hack everyone's credit card if you answer that question. Let's put it that way. So you'd be a trillionaire. And the maths people will also give you $1 million, which is a bonus. So yeah, that's pretty brief history of primes and where we got to, where we are today. Basically, a lot of the things that were discovered in the 17, 18, 1900s, the Riemann hypothesis is still one of the fundamental questions that haven't been proven. And there's this institute called the Clay Institute for Mathematics, and they're offering $1 million for the first person who proves that the Riemann hypothesis is true. So it's quite an important problem to mathematicians.
So Riemann is every prime number is the sum of.
And that's not Riemann. We'll get to Riemann. That's Goldbach. So that doesn't come with $1 million, but they also want to solve that.
Riemann, can you repeat what it is?
We'll get to that later because it's not like a single statement. Well, it is, but we need to do a few things first to understand it.
I just wanted to make sure I hadn't missed.
Yeah, we'll get to it. Yeah, don't worry. Yeah, so Riemann, intuitively speaking, Riemann talks about the distribution and the pattern of the primes, but it doesn't give a single formula for it. But we'll come back to it because it's confusing. So yeah, to summarize the primes, in the primes we have this mystery of how do prime numbers actually behave. So we know there's an infinite number of prime numbers, but we have computer programs to keep finding larger primes, but we don't have a single understanding of what the pattern is in these prime numbers or a single formula that tells us which number comes next. That's really the big mystery. The elegance is this search for solving the Riemann hypothesis to have a proof or understanding of what is the behavior of the prime numbers. And the utility, we'll get to that also later, but basically prime numbers are involved in a lot of important computer systems today, mostly in how cryptography works. So how the way your bank account transactions are secured, for example, has a lot to do with prime numbers. But again, we'll get to that later. But firstly, let's do a bit of a puzzle because I feel like I've been talking for quite a long time. So now that we understand what the prime numbers are, there are 3 prime numbers, and these 3 numbers add up to 100. One of these numbers is more than a third, but less than a half of another. What are these 3 numbers? So I'll give everyone 5 minutes to think about what those sentences mean and come up with some answer. It's a bit of a tongue twister. Okay, I'll set a 5-minute timer, but if that's not enough, someone let me know.
If I ask Siri that question.
Maybe she'll respond.
Will she answer?
Siri is done anyway. So
3 prime numbers that add up to 100. One of the numbers is more than a third, but less than a half of a number.
I guess you just ask the 3 that add up to 100. Cheat.
Cheating.
Fascinating.
Oh, and if you want, you can Google like a list of prime numbers. Don't.
Ah.
Yeah, that's allowed. Just don't Google the whole question directly.
Ah. Sorry. Channel my energy.
That's all good.
You cheated.
Это значит, складывать эти суммы, они будут в результате 100. То есть 3 числа, которые будут потом 100. Okay, so I can Google prime numbers.
Yeah, you can Google like a list of prime numbers.
Okay. Sorry. Less, when you say less, is it?
Or smaller than?
Strictly less?
Yes, strictly, yeah.
Yes, well, you didn't precise, so I found a satisfying answer.
You mean it's not random numbers, it's these numbers what are suitable for this condition?
Yeah, so it's not
or
just...
they are only 3 numbers what are add up to...
There may be other combinations that add up to 100, so they also have to satisfy this second sentence.
It's so complicated. It's so hard.
Less means less. I don't know, maybe in French. In French, when you say it's less, it's implied less or equal. And if you want it to be strictly less, you have to say maybe in English.
Oh, okay, maybe I can... Did you find an answer where it's like equal? Okay. And maybe I can allow that. Yeah, fair enough.
But I don't know, in English when you say less, does it
means-
strictly less?
It means strictly less,
Okay,
yeah.
so it's different.
Because if you had less than sign,
French people are very
Less than or
optimistic,
equal to.
aren't they?
That's, yeah.
yeah, we would say like less than or equal to.
Okay.
If you just said less than, it means it has to be
In
strictly less
France,
than.
when you round the number, do you round it to the like a lesser number or to a higher number? Let's say
Man,
0.0. It's like 1.5. Is it? If you round it, is it 1 or is it 2?
2, of course.
Russians round it to 1.
What?
Mm-hmm.
Ah, you mean okay, interesting. But the explanation is
Russians are pessimistic.
every prime number is the sum of 2 prime numbers. Right.
Every even number. Oh,
No.
which one's this?
Goldbach.
Goldbach is every even number is the sum of prime numbers.
Ah, yes.
Not two prime numbers, yeah.
And every prime number is the sum of 2 prime numbers. It exists, or
Not that, no. Only even numbers.
that's my
Mm.
mistake. Okay.
But every number is you can multiply.
I found only one, and I don't know if it fits this condition.
We've got 3 seconds
I
left.
found one. Oh, yeah, me too. Boom.
Okay.
Okay.
Ah, stop.
No, it's good.
Okay, who was able to answer the question is willing to share their answer.
Okay. This is good or not?
Yeah, let me-
Last one.
Right now. Thing is annoying. Okay, what is your answer?
1979.
297.
19,
Oh.
1979.
Yeah.
If I'm not wrong in arithmetic.
I think maybe perhaps according to the
219.
regulations, it has to be more than a third but less than a half.
I couldn't understand. It's wrong, yeah?
Yeah,
They add up to 100, but it doesn't meet the
the criteria.
criteria
What
here.
is the wrong there? So
Yeah, so we can go through it.
The second
It's
number.
more than a third.
So
one of the numbers.
one of the
is more than
numbers
a
is
third.
more than a third,
It's
but
true.
less than a half of another. So in your case,
More
Yes, it's true.
so you're saying
I doubt that.
no, it's not.
More than a third.
It's true. It's more
But it's
than.
not. It's not.
This one is more than a
It's not.
third.
It's not
Ah.
more than a third. No,
So you're saying this
no.
one's more than a third, but less than a
It's not
half.
more than that.
No, it's not good.
No, it's a third of 79. What's that?
Can you show me once more?
Yeah.
But less than half of another.
I didn't find
It is
it.
less than a half, but it's not more than the third.
No more than a third. So if you divide 79 by 3, 19 is less than that. Does that make sense?
Can
Maybe
you-
I wasn't that convinced.
It needs to be more and less at the same time. And in your case, it's both less and less. I don't know if it makes
Okay.
sense. Yeah, that's it.
No, less
No,
than
it
that.
doesn't.
Both.
I'll go for one answer that works. So the answer I've got is 31, 67, and 2.
Not good.
I got 61, 37 plus 2.
61, 37, and 2. That might work as well. Let me figure out what a third of those are so it doesn't go evenly. Where's the calculator?
It should be less than a half.
So for 67,
Can you rate me these x by z? What should be less and more in ratio?
this is more than a third.
X, for example, I have
It should be
x is more.
So
is
less.
a third
don't
of
remember
this
now.
is
y must be
22-ish.
less than that. For example, third one,
1.5.
and at the same time more than 2. No, I don't know.
So in this case here, a third of
More
67.
than half of this.
Oh,
Yes.
yeah. Does that make sense now?
Yeah.
So for this answer, a third of 67 is around 22 point something, and a half is around 33. So because it's the 31 is in between those two, that meets the condition. Yeah. This one here. So a third of 61 is around 20 point something. Half is 30 something, No, it's still too small. So this number here it doesn't work because it has to be in between these two. So that's the reason why that wouldn't meet the condition. But yeah, it's a tough problem, and it doesn't help that the wording is deliberately confusing to try and confuse you.
Oh.
But condition is but less than a half of another. What is this half of another?
So you have to pick the other. Yeah, so any of those. So in this case, we call the another one, like this one. And so there has to be something else, this one here, that's more than a third of 67, but less than a half of 67. So because 31 is in between 22 and 33, it meets the condition.
So it's more than half of another.
Yeah, so it's more than 33, but it's less than 22. Sorry, other way around. More than 22, less than 33.
Make me think.
It's one of those things that kind of gives you a headache after thinking about it for a while.
See that you enjoy it.
And the most important question: if I'm constantly failing with these kind of questions, am I a bad mathematician?
No, you're not.
You're
Just bad at solving riddles.
So the road is closed for me.
No.
This looks like the kind of crap that would give you like a good old job.
Yes, it is. I think it's one of those types of questions. Oh.
Which also tells you nothing about how good of an engineer you are.
But that's the
I think they stopped doing that at Google though.
They stopped doing that, I think.
Yeah.
Ah, they stopped?
Yeah. Well, because it's done.
Yeah, it was a stupid idea.
Google?
Yeah.
Okay.
Okay. Any more questions about the puzzle? Or are we good to move on?
No,
Cool.
let's move on.
Please, I suffer.
Yes.
So the final topic we do before we go into the complex numbers is going to be about proofs. We can either take a bit of a break now and come back and do it, or do you want to do proofs before we have a break?
Let's
How does everyone feel?
Yeah.
Okay, cool. So I spoke a lot about theorems that are proven or not proven yet, but I didn't really explain what does it mean to prove something. So this is the point of this section, to explain this in a bit more detail.
Okay.
Anyways,
I thought that would be a donut there, but yeah.
Ah, donuts.
What?
Yes. You could bring donuts next time.
oh yeah, it's like donuts.
To
And,
topology.
am I making people hungry by having donuts on the plate?
Topological donuts.
Yeah. So basically what a proof is, it's just an argument that's constructed to convince other people, or other mathematicians, that something is true. And in mathematics, we use logic to make that argument. And so if a proof is good, then it also should try and help us understand why that thing is true. So we may have a problem where we have a proof, we may have multiple proofs that prove the same thing, but some proofs are better than others because some of them are more descriptive about the actual underlying mechanism of what's going on in the problem. So in terms of the language of proofs, we use formal logic, and every proof starts with a statement of the thing we're trying to prove. So for example, in notation, we could say there's a statement that we call P. It could be any statement, like the sky is blue is a statement. And we have to try and prove that. And so in logic, we can prove that is true by a number of ways. One of the most common ways that I'm going to go into with an example is a thing called proof by contradiction, which is where we start by assuming that the opposite of the statement is true. So if we're trying to prove that the sky is blue, let's start by assuming the sky isn't blue. And by proving that it couldn't be true that the sky is not blue, we end up proving that the sky is blue. So it's a bit confusing to get your head around, but basically you can think of it as assuming that the opposite is true and proving that is wrong. So the example we're going to go into, we don't need to worry too much about the logic and notation. The aim today is not to understand that too much.
You try to prove that it is not blue, yeah?
Yes, proof by contradiction. So we want to prove the sky is blue. We say the opposite, the sky is not blue. If we can prove that we can't prove the sky is not blue, then it proves the sky is blue.
What is interesting? It's methodological trap maybe.
It's like the inverse. You're doing the opposite. By doing the opposite, you come back around to the other way.
I highly recommend formal logic. It's quite a bit of a mind fuck.
Even Aristotle would use it. Interesting. Yeah.
So yeah, so we're not going to do too much on all the notation and stuff. We're just going to look more at the ideas behind it. But we're going to look at an example of this proof of contradiction by proving something is true, by taking the opposite, and by proving the opposite is false, deducing that the original thing we want to prove was true. So basically how this works, we take some statement. The example we're going to use is the proof that there's an infinite number of prime numbers, because that's one of the most famous proof by contradiction proofs in mathematics. So we can assume that the statement is false. So if we want to prove there's an infinite number of primes, we can do the opposite and prove there's a finite number of primes. The number of prime numbers is fixed. And then we have to take that assumption and deduce some kind of contradiction to that. So basically prove that the opposite of the thing we're trying to prove couldn't possibly be true. And then by assumption, that ends up proving the original thing is true. So I know that still sounds very abstract, so we'll go into an actual example to hopefully give some more clarity to that. So infinitely many primes. I'll draw some stuff on this pad as well. So the thing we want to prove is that there's an infinite number of prime numbers, that the number of primes just keeps going on forever and ever, and there's no end to that pattern. And so by proof by contradiction, the first thing we have to do is assume that the statement is false. So assume the opposite, that there's a fixed number of primes. And then we have to deduce that isn't true, and then the opposite will occur. So there are two famous approaches to this. The first one is by Euclid in ancient Greece, and he said, okay, let's suppose that there's a fixed number of primes, and let's notate these primes. So I'll write it here. So there's some prime, P1, prime number 2, prime number 3, prime number 4, and so on. And because we're assuming there's a finite number of primes, the number of primes is fixed. It comes to an end. So there's some number n for which we reach the end of the prime numbers. So this is by assuming, assuming finite primes, which is the opposite of what we want to prove. So now what we have to do, we have to assume that this is wrong. Well, we have to, prove that this is wrong. And by proving this is wrong, it proves the original thing, that there's infinitely many primes, is right. So what Euclid did, he assumed there's a fixed number of primes, there's n prime numbers. And then he took these numbers and he created a new number by multiplying them together and adding 1 to that. So here, he invented a new number. He said, let's call that P. And let's multiply all the primes together up to n prime. And let's add 1 to that. So that was his first step. And then he asked, is this number a prime number or is it not a prime number? Because if our assumption is true and n is the largest and last prime number, it can't be true that this is a prime because this number is larger than n. So he had to prove that this is wrong, and that basically proves the other thing is right. So let's go through that. So I haven't got it in here. So basically, we have to figure out what this number is. Is this prime? Or is this not prime?
Really depends from members of multiplication.
Yeah, so if it's prime, then it means that there's no other factors that divide into this other than 1 in itself. If it's not prime, that means there must be something else that divides into this number. So let's assume that for the case that it's prime, for example. But we know that let's assume it's not prime. Because if we assume it's prime, then it falsifies the statement because this is larger than the last prime. So we have to keep assuming this is not prime for the thing we proved, or thing we assumed here, assuming finite primes, for that to hold. Mm-hmm. So we assume it's not prime. It means there's something that divides into that. But if we look at this number, we know that none of the primes, so none of the P1, P2, P3, can divide into it because there'll always be a remainder of 1 if we divide into that. There'll always be some kind of remainder just by the way we constructed that number. Does that make sense? Yeah, so basically, if you try and divide P2 into this thing, there'll be P divided by P2, there'll be P1, P3, all the way up to n, plus some kind of remainder there. So we can't divide it by that. So by construction, this number can't not be prime. It has to be prime itself because they can't find anything that divides evenly. There's always going to be this kind of remainder thing. So therefore, the number has to be prime because of that.
Do you say in English absurd proof?
Proof by absurdium? I think that's a Latin.
Proof by absurd.
Yeah, I've heard the statement, proof by absurdium. Yeah.
In French it's pretty... Okay.
It's like Latin, I think.
But if there is a prime, 2 is a prime number.
Yes.
Yes.
So it's that's one of these ones here.
Yeah, if it's a multiplication member, then it can be divided by 2.
Yeah, but it's one of the ones here. So
yeah, so plus one.
Because we've assumed these are all the primes. Prime is like P1 could be 2, but we can't divide this by P1 because there'll be this remainder because the way we constructed this thing.
Okay, but it can be divided by 3 then.
No, because 3 is one of these. Because that's what we define here by saying this is the list of prime numbers. 3 and 2 are already in this list.
Why? Okay.
Because that's the assumption we made. We assume this is the list of prime numbers we know.
Yeah, but 3 is there. But what
In
will
this list,
happen if we will divide by 3?
So if we divide by 3, there's a remainder because of the way we constructed this thing. So if you divide things, so P divided by 3, we have this whole sum here. And we want to divide that all by 3.
Mm-hmm.
3 has to be one of these primes. So 3 might be P2, for example. It has to be in this list of P's.
Mm-hmm.
That's because that's just the assumption we made.
Yeah.
Yeah. So we divide, if we say, for example, 3 is actually P2, we can divide out the P2. But there's still going to be like this kind of remainder thing here. Because you have to still divide the 1. Does that make sense? You can divide the P2 into the P2 and get rid of that to get that, but you're still going to have this plus thingo at the end. Like there's still plus something. So it's not going to divide evenly.
But it's not the integer now.
That is. By construction, that's an integer. And that's not an integer. Yeah, exactly. So it's not prime. So the assumption is wrong that we can't divide into this thing. So by construction, this thing is not divisible. And so this thing here has to be a prime number. But then that contradicts our first original assumption that this was the last prime number. But because this is larger than that, there must be another prime number. There's me like PM that's larger. And so by the existence of there being something that's larger, by the way we constructed this, it must be the case that there's more primes, that our assumption that there's a finite number of primes is false. So I know it's a bit confusing, but basically the gist of the proof is assume there's a finite number of primes, assume we can't make a prime number bigger than this, but this number here is an example of a prime number that's larger. So it's proof that there must be another larger number.
Mm-hmm.
So therefore, this is wrong, and we conclude that there's infinite number of primes. That's proof by contradiction.
Let's continue, but I will validate this.
Okay. You can go argue with Euclid from ancient Greece. You're all wrong. So yeah, basically, even if you don't understand all the details here, the whole concept is assume the opposite of the thing, prove that is wrong, and by proving that is wrong, the original thing's true. Yeah. So and as with everything in mathematics, go back to the slides. Cool. There's always another way. Someone's found a different way of doing the same thing. And so Euler in the 1800s, or wherever he's from, he found a second way of proving the same thing, which is much more complex. I'm not going to go into too much detail here because this involves a lot of algebra. Basically, the mechanism by which he arrived at the same conclusion, he also used a proof by contradiction, but he also was using a function that's quite famous in mathematics called the Zeta function. And so basically he was able to prove that there's an infinite number of primes by constructing a series out of these prime functions. So mathematics, there's a few famous series. One is the geometric series, when you add these numbers together in succession and keep raising something by the power of a number and keep going. And there's also something called the harmonic series, this one here. And so by using these, he was able to prove that the number of prime numbers is also infinite, but using a different approach. And so one of the key things here, we won't go into this proof itself because it takes quite a lot of time to understand a lot of the algebra involved, so we'll skip over that. The important takeaway was that he was using something called the Riemann Zeta function, which is this one here. So this is quite scary looking, so I'll write it out a bit. Not this one. So this symbol here, which I can't draw, is zeta. And S just means a function of S. And in the notation of the function, it's a sum between n equals 1 to infinity of 1 over n to the power of s. So what does this mean? This symbol here, this one here, it just means sum. So it means add things up. So what it means is the thing at the bottom here is like your lower bound and this is your upper bound. So you want to add something up in between 1 and infinity. And the thing you're adding is this thing here. So what we're doing, we take 1 over n to the power s for any value of s, and we go between n equals 1 to infinity.
And see what happens and expand that function. And so during all this time, they looked at what happens if s is a real number, so an integer. But there was Riemann who then asked the question, what happens if s is a complex number? And so complex numbers is the next section of this talk, which I think we'll take a break first.
Oh, yes.
Yeah, so we're quite hard. But basically, after that break, we're going to go back to this function and understand firstly, what is a complex number, imaginary number, what that is, and why does it matter that we're asking the question, what happens if S is imaginary? So that's...
Applied reason, let's have a break.
Yes, let's have a break.
Yeah.
Applied.
And we can have some questions if you didn't understand something.
Yeah.
We can chat also.
We'll come back in about 20 minutes.
20? Yeah.
Go downstairs.
Cool.
If you want as well.
Hey
Take a
Siri,
look.
put. It doesn't want to talk to
That way.
me or Siri, both. I'm waking you up. It's nice.
So we start back in 10 minutes.